line connected to our repeated squaring, right? I think you remember that repeated squaring. Yeah. How powerful it is. But here, a similar technique called a repeated cubing technique. Squaring and cubing, right? Yeah, similar. Yeah. The reason I need to talk about that because this one, sometimes it can do better than repeated squaring. So that's why I may like to introduce this repeated cubing algorithm. All right. Let us still study this general formula, polynomial, Horner's rule in general, right? Yeah. When we have one term, the exponent is power of 2 based on our experience discussion in part C, we know we should use repeated squaring. Yeah. But here, another question, related question here, how about when n is power of 3? N equals 3 to the kth power. It's a power of 3. This time repeated squaring may not be better than cubing. 3 is up to 2. How about it? Okay. All right. So in order to show you the difference, all right, let us consider n equals 9. 3 squared. Okay. 3 squared. The first time, let us use repeated squaring to do it. And see what is the best repeated squaring. Although it's not power of 2, but we can use as many squaring operations as possible, right? Yeah. So it's not a power, here. This number, not a power, let me write power of 2, but we can apply the repeated squaring as many as we can. The greedy approach. How about a greedy approach? As many as we can. We know it's a useful tool, so when we use it, use as much as we can. All right. So let's try it. Okay. Yeah. X times x, the first multiplication, we get s squared. Okay. So this is our first multiplication. Next, x squared times x squared, the second multiplication, we get x to the 4th. That's our second multiplication. Then x to the 4th times x to the 4th, we get x to the 8th, our third multiplication. All right. The last one, x times x to the 8th, that is x to the 9th. So the last one, total 4 multiplications. How about that? By repeated squaring operations, the best we can do, 4 multiplications. 4. Okay. All right. Now let us try repeated cubing. Repeated cubing. All right. Yeah. Okay. Yeah. The first one still x times x squared. Yeah. The same as before. For the second one, we need to get cube. X times x squared. We need to get x cubed. All right. Okay. Next, the last one. Also for the same as repeated squaring, also for this example, looks like the performance are the same for these two. If we go to some other examples, we will see the difference. Sooner or later, you will see the difference. But this one, at least you see there is another method you can get the same efficiency, right? Yeah, cubing. So let us do another one, see if we can do better. Yeah. We want to find the one with repeated cubing doing better than repeated squaring. Okay. First, I want to try 15. See what happens. 15, because 15 is multiple of 3. 15 is multiple of 3, then repeated cubing should have some advantage. Repeated cubing should have some advantage. But let's try repeated cubing first. All right, yeah. Let me just put a cubing here. Cubing method here. Yeah. The first one, x times x, we get an x squared. Second multiplication, x squared times x squared, we get x to the 4th. Then the third one, x times x to the 4th, we get x to the 5th, the third one, right? Yeah. The next one, x to the 5th times x to the 5th, x to the 10th, 1, all right? Yeah. The last one, x to the 5th times x to the 10th, x to the 15th, 1, yeah. Total number 5. All right, repeated cubing, total number 5 here. Okay. Now, repeated square. Let's try repeated square. All right. Still, x squared, the first one, x squared, x to the 4th, second one, x to the 4th, x to the 8th. Oh, sorry, second one, I just put a 1. Yeah, accumulative, yeah, 1. Okay, all right. So the next one, yeah, because we cannot do another squaring, then we get x to the 16th, right? Yeah, so here, how should we reach? One way, x to the 4th times x to the 8th, get x to the 12th, right? Then x squared times x to the 12th, x to the 14th. Another one, right? But we need one more, x times x to the 14th, x to the 15th. One, right? So total, you can see we need 6 comparisons, 6 multiplications. Look at that. Can we do better? I think that's the best we can do using repeated squaring, right? Yeah. Because at some point we cannot do squaring more, so we have to do multiplication using the existing numbers. So we need 6 multiplications. But repeat cubing is better in this case 5. 5. Look at that. Another example, 27. 27 power of 3. So definitely repeated cubing can take advantage the most. If you try repeat squaring, so you power 8. You need more multiplications. You need more. So here you can see at this point, after we do the repeated squaring and the repeated cubing, do you have some idea for the general case and for the general case and you can see there are 2 methods, 2 efficient methods you can use. But which one gives you the best performance? That question is not easy to answer. Right? That question is not easy to answer. So here there is a general question. I do not know the solution myself. The general question is like this. Given general n, arbitrary n, positive integer, arbitrary positive integer n. How to get the fastest fastest computation or smallest number of multiplications to find x to the nth power. So here's the question. So the goal is very simple. Our goal, we want to find x to the nth, this value. What is the fastest way to find it? You can choose repeated squaring. You can also choose repeated cubing, and you can mix them. How about that? You can mix. Yeah. For some terms, use repeated cubing. Some terms, repeated squaring. You use both. It's both. Your goal, get a minimum number of multiplications. This question, I cannot solve myself. I cannot give you a clear answer how to solve it. It is an open question for me here. For me. Open. Challenging, very challenging. All right. But in our textbook, actually, we have a related algorithm that gives us implementation of the repeated squaring, not repeated cubing, repeated squaring. So there is some interesting implementation we can use. We will study that one. At some point. We will study that. All right. Okay, yeah, so here. Before we finish today, it looks like we have about 5 minutes. Yeah. So let me see if